When we heat things, the temperature usually increases. By doing experiments, scientists were able to figure out how much we need to heat something in order to raise its temperature by some number. Specific heat capacity is a way to represent this ability of substances to absorb heat and raise the temperature. In formal definition, specific heat capacity is the amount of heat needed to raise the temperature of 1 kilogram of matter by 1 degree Celsius or 1 Kelvin. Or C is equal to Q by M delta T. So we can calculate the amount of heat that has been added using the equation Q is equal to mc delta T. This value of heat depends on the specific situation of heating and many other variables. So, there are two types of specific heat capacity, depending on how the heating takes place. If the heating happens at constant volume, we use specific heat at constant volume, written as CV. If it happens at constant pressure, we use specific heat at constant pressure, written as CP. Since this heat is completely used to change the temperature of the system, specific heat is an easy way for us to measure the increase in internal energy and the enthalpy of the system. The ratio of these specific heats is denoted by gamma. This is constant for a given gas and depends on the number of atoms in one molecule of gas. For a monoatomic gas, that is whose molecules have only one atom, the ratio of specific heats is 5/3. For a diatomic gas, that is whose molecules have two atoms, the ratio of specific heats is 7/5. Similarly, for triatomic gases, gamma is 9/7 and so on. There is another equation, called Meyer's relation, which says that Cp minus Cv is equal to our specific. Using these two together, we are able to get the value of Cv in terms of the specific gas constant, and gamma. And Cp is just gamma times the value of Cv. Using these relations, we can calculate the specific heats for any substance, as long as we know the molar mass, to calculate our specific, and whether it is mono, di, or triatomic, to calculate gamma. Some values we need to know by heart are the Cp and Cv for water, which is 4.2 and 2 kilojoule per kilogram Kelvin, respectively. And also that air, since it is mostly made of nitrogen and oxygen, is considered as diatomic, with an average molar mass of 28.97 grams per mole. So, our specific is equal to 287 joule per kilogram Kelvin, and gamma is equal to 7/5, or 1.4. Using these, we can calculate the values of Cp and Cv.